Please run the seminar. Please run the seminar.
What did you say?
Okay, you may introduce Mithun and run the seminar.
No, it doesn't matter who introduces. Okay. No, you can start. I'm just joining on and off, right? So.
Okay. Okay. Welcome back to our APRG seminar. So it is my pleasure to introduce today's speaker, Mithun Bhowmik from IIT Kharagpur. The title of his talk is Uniqueness Results for Quasi-Analytic Functions on Compact Lie groups and Homogeneous Spaces. With this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphone. So over to you, Mithun.
Okay. Okay, can you hear me, Mona?
Yes.
Mona, can
I can. Yes, we can hear you.
Okay. Good afternoon, everyone. So I would like to begin by thanking the department for giving me the opportunity to talk about our result here. So today I'll talk about uniqueness results for quasi-analytic functions on compact Lie groups and their homogeneous spaces. So motivation of this work comes from the fact that how to quantify the unique continuation property of analytic functions. And this is also related to the Ramage type inequality, and also a well-known fact that propagation of smallness to the solutions of certain elliptic PDEs. So let us start with what is Ramage inequality. This is a classical result. So in some sense, Ramage inequality tells about the polynomials, that how can we control a polynomial over an interval by its behavior on a positive measure subset of that interval. So let's say P be a polynomial of degree n, and any interval I will take a positive measure subset of I. Then I can control the L infinity norm of this polynomial by the L infinity norm of its restriction on the positive measure set. So the constant that of course will depend on the measure of the set, and the constant that appearing in the index, that is nothing but the degree of the polynomial. So this result is actually the quantification of the fact that a polynomial of a degree cannot have a root of multiplicity more than the degree. This also tells how a polynomial can vanish or it can decay on a positive measure set. So this is a quantification of these facts. Now, how to prove this inequality? Okay, the standard and very classical one is to use the polynomial interpolation of this polynomial. So we can interpolate this polynomial by choosing the nodes points at these positive measure sets, and we can choose the number of nodes which is greater than the degree. Then we can use the expression of Lagrange or polynomial interpolation, and then we will get this result. Okay, this is a classical result. So one can prove this result. So now instead of polynomial, can we assume a more general class of functions? Yes, we can assume. So let's say we'll assume the analytic functions. Okay, so now I'll replace the polynomial by analytic functions. So function now is analytic in a disk. That disk has to be sufficiently large, and that contains the interval -1 to 1, and it's at origin. Let's its value is greater than 1. Now I'll take any positive measure subset of -1 to 1. Then the restriction of this analytic function on the interval -1 to 1, this L infinity norm will be controlled by its restriction on this. So I should not write it E here. It is A. So L infinity norm of F, its restriction on the set A. So the polynomial we can now extend it for analytic functions. This one is also very classical result. And the index that appearing here is the supremum norm of the function over the entire disk. Now one of the method that one used to prove this inequality is to use the Harnack inequalities for positive harmonic functions. So using Harnack inequality, that is also applicable for harmonic functions, and one can use that inequality to deduce this. So this is a generalization of Ramage inequality for analytic functions. Now the use of harmonic function that actually leads to a generalized fact that, okay, instead of the analytic function, can we consider any solutions of elliptic PD? So that still can we get an inequality like that? So this inequality, this kind of inequality in the classical sense, one can say that this is the smallness, the propagation of smallness. So what is the smallness? If the function f is sufficiently small on a very small set, then this smallness will be propagated to the entire interval -1 to 1. So in the previous case, the smallness of the polynomial on a positive measure set can be propagated to the whole interval I. So in the same sense, here the analytic function, the smallness will also propagate. So there is a breakthrough result due to Lagunov and Melinkova in 2018, where Lagunov proved this result, and this result appeared in the proceeding of ICM 2018. So this analytic function now he replaced by a solution of elliptic equation with a limited regularity on the coefficient of the equation. So this is a much more general class of functions, not only analytic, but they are not analytic, but they are solution of certain elliptic equation. Still, this kind of inequality also holds true. Now, what should be the constant that appearing at the index? It should they actually prove it, so it will appear like the doubling index of the function. So it has an application.
Mithun, since I'm new to this constant C depends on the size of the disk or only on the interval -1, 1?
No. This C will depend on the interval -1 to 1, and that disk actually will be constructed out of the interval -1 to 1. So the radius of the disk will depend on the Harnack inequality, so that I can apply that inequality. So disk, we can choose the minimum one, but the constant C should depend on the interval -1 to 1. Okay. So in some sense, disk and the C, they all are depend on the interval -1 to 1.
Okay.
Okay. Now, so this is the classic. This is the results about the smallness, propagation of smallness. So now I will come to certain uniqueness results. That is also a quantification of uncertainty principles in harmonic analysis. So this result is due to Logvinenko and Sereda. So to state that result, so I'll say something about the relatively dense subset of R, okay, or RD. Okay, some subset on RD is, sorry.
Can you hear me? The previous
Yeah.
result. In the previous result,
Yes.
yeah, here if is analytic in any disk containing closed -1, 1, or you are talking about a particular disk D?
Actually, I should have written it here. The radius of the disk should be strictly greater than 4. That 4 actually coming from the Harnack inequality. So I should mention the disk. This should be centered at origin of radius at least 4. So it should be, the function should be analytic in a disk of radius 4. And then we can talk about the restriction of f on the interval -1 to 1.
Thank
like
you.
that. So now I'll talking about some uncertainty principle on this is regarding the this is related to the Logvinenko-Sereda theorem. So before that, I'll start with the definition of relatively dense set. So what is relatively dense set? So a subset of RD is called relatively dense if I take its portion on any cube of side length, let's say L, then it should have contain a mass that proportional to gamma of the size of the cube. So this relatively denseness will be parameterized by two constants. One is gamma, other one is L. L is related to the side length of cube, and gamma is the portion of the mass of the set E that should be contained in each cube of side length L. So it is relatively dense. So it is spread enough on the entire Euclidean space. Now, Logvinenko-Sereda theorem talking about the function which are spectrally localized. Then we can propagate the smallness on a relatively dense set on the entire Euclidean space. So this is the exact statement of the result. So we fixed a subset in RD then for every n positive, there exists a constant C. That C will depend on n and the set and the not exactly on the set E, but on the parameter gamma and L, such that whenever we will take the L2 norm of F on the entire Euclidean space, that will be controlled by its L2 norm on the restriction of relatively dense set. For all functions which are spectrally localized, in some sense, its Fourier transform has to be contained in a compact ball. So these functions are essentially in the polynomial space. So whenever we have a function in the polynomial space, its support should be spread enough. So on the other hand, we can extract the L2 norm of the function from a relatively dense subset of RD. So this is a statement, and this statement is if and only. This is sharp statement. Whenever we have a statement like this, that E has to be relatively dense set. And converse is follows from the classical polynomial theorem. So now this entire statement can be translated in the setting of Hilbert space. So what is the statement here? So I'll consider only a self-adjoint operator H that is acting on L2M. M basically will take a Riemannian manifold or something like that. Then this is a Hilbert space on which a self-adjoint operator acting. Then I'll take a subset of M. That should be that I should impose some condition on the subset S later. But if there exists some constant C that depends on the subset and some energy E, so that whenever we have a function that is spectrally restricted, so I'll take the function whose spectral projection go up to the energy E. So on the spectral side, I'll take the projection up to energy E. So if I consider all those functions, then I can recover the L2 norm of the entire space M from its L2 norm on some subset S. If this kind of inequality is true, then I'll call this set S satisfy the spectral inequality. So of course, this condition that F is spectrally restricted, this translate in the Euclidean setting, its Fourier transform is compactly supported. Then we know that Logvinenko-Sereda theorem says that okay, S has to be relatively dense. That is the if and only if condition. So now it has so many applications in applied mathematics and in other areas also. So Hilbert space setting is much more applicable there. So this is a statement of the theorem. So now I'll talk about some recent result on this topic. Okay, so as I said, the Logvinenko-Sereda theorem appeared in 1973, and its proof uses the complex analysis techniques and a small propagation of smallness for analytic functions. That was the main ingredient to prove this Logvinenko-Sereda-type result. And Kovriskin in 2001, and he proved a sharp constant that appearing in the inequality, Logvinenko-Sereda inequality. So he actually proved what is the sharp constant in the inequality. Now, in 1999, so there is a paper in conference proceeding, Jerison by Leview. They actually shows how the propagation of smallness for harmonic function can be applied to the spectral inequalities. So it has an application to controllability, to observability problem, for heat equations, and like that. And also it bound the Hausdorff measure of the nodal set of corresponding eigenfunctions or harmonic functions. So it has applications. So spectral inequality is related to the propagation of smallness of harmonic functions. And 2020, so this same spectral inequality is proved for d-dimensional torus, and it has application for the related to the uncertainty principles in the context of random Schrodinger operators, and also Wagner estimates is there. These things are coming as an application of spectral estimate on d-dimensional torus. So now we will consider the compact manifold. Now, if a manifold is compact, so if we assume that the manifold is so Riemannian manifold and it is analytic manifold, then there is a famous result by Pfefferman and Dulini, and they prove a similar kind of uniqueness result. Not uniqueness result, similar kind of propagation of smallness result in the context of analytic manifolds. And as I said, the Lagunov and Milenkova's result in 2018 was for smooth manifolds. So on the smooth manifold, one can use one can prove a similar kind of propagation of smallness result. Now in 2023, Burg and Marno, they prove a spectral estimate for Laplace operator on a compact manifold, but with a limited regularity on the metric. So we'll consider only the Sobolev to infinity manifolds, but still the propagation of smallness is true there. So this is the result that that his student, the student of Burg, Revelon, he proved a result about the spectral estimate on the hyperbolic plane. So this was the first result, some kind of spectral estimate that holds true beyond the Euclidean space and any perturbation of Euclidean metric. So this is a purely non-Euclidean phenomena where the exponential, where the volume of ball grows exponentially. So this is not an Euclidean space. This is not a perturbation of Euclidean space. This is not a compact manifold. So this is a genuine result on a geometric result that is holds true for non-compact manifold, but an hyperbolic, and this its metric is related to the hyperbolic metric, but this is on the hyperbolic plane. So what is the idea of the proof of his result? The same result, the same Logvinenko and Menilkova's result. So this is the propagation of smallness for harmonic functions. So we'll consider the Laplace-Beltrami operator on the hyperbolic plane. Then I'll write down the Laplace-Beltrami operator in the coordinate axis, and then whatever we'll get that operator, that will be nothing but a elliptic operator. And that the coefficient of the elliptic operator will satisfy the condition that was assumed in the result of Logvinenko and Menilkova. And therefore, we can use readily the Euclidean result. And then we can prove a propagation smallness for a hyperbolic plane. Now, hyperbolic plane also we can break the entire plane with non-overlapping or limited overlapping balls, and then we can accumulate the entire thing, local estimate to the global estimate. So this was the idea for hyperbolic plane. So this is a story or kind of propagation of smallness for the function which are spectrally restricted. Now I'll consider the function which are not spectrally restricted. So spectrally restricted means we will consider a function whose Fourier transform is compactly supported. Now let's say we are not considering the function whose Fourier transform is compactly supported, but it has certain amount of rapid decay at infinity. So can we still say something about this smallness result? Yes.
In this idea, which has been applied on hyperbolic plane, why it doesn't go to higher dimension, hyperbolic space, real hyperbolic spaces? What stops me?
Okay, so first thing is that this Burg and Mano, their result is for compact manifold. So on hyperbolic plane, I have to prove the result only locally first, and then I will translate these local balls to cover the entire plane. So this covering phenomena is highly volatile for high dimensional hyperbolic spaces. So I cannot didactically decompose the entire plane hyperbolic space in small rectangles or balls. That one problem is there, but can we still obtain the local result at least on hyperbolic space? Okay, to obtain the local result, I have to write down the Laplace-Beltrami operator on the higher dimensional hyperbolic space, like a elliptic PD. So to writing down, their coefficient should be related to the quad hyperbolic and these kind of functions. To manage them, and there we should have some uniform control on the coefficients. So I think little bit problem is there to obtain the local one also.
I see.
So these are the problems still there, but I'll talk about this later at the end of this talk. Okay, so now I'll talk about a function which has sufficiently decay, not compactly supported Fourier transform, but sufficiently decay Fourier transform. Still, can we obtain a smallness result? Okay, so to start with that direction, we'll start with this following result. So here we have a parameter gamma, and we have a subset of R that is gamma 1 relatively dense set. So whenever I'll take a unit length interval, I intersect it with U, then I'll get a gamma portion of that interval. So that is the relatively dense net. And we have a delta, and then we define a theta xi, a function that behavior is logarithmic xi to the power minus delta. Now this is the result of Burg. So this result I already have we already have talked about this thing in last conference in Bombay. Some of you might have seen this result. So it says that whenever we have a relatively dense set, that relatively denseness is coming, that parameter is coming like this gamma, and we have a C. That C is coming here. So we have a function whose Fourier transform decay rapidly. So how much its Fourier transform is decaying? So we can still get Fourier transform times exponential of mod xi and times theta xi. Theta xi is this quantity. If its Fourier transform has this much decay, then I can still get the some control of L2 norm of the function out of its L2 norm on the relatively dense set. So this leads to the fractal uncertainty principle on R, and this proof actually usually use two crucial ideas. First one is that whenever a function has this kind of decay, it will be a quasi-analytic function, something called quasi-analytic function that I will define in a moment. So in some sense, it cannot vanish on a positive measure set. So this result is a quantification of this fact. And also this result use this fact that so whenever we have a compactly supported Fourier transform whose compactly supported function whose Fourier transform decay like that, then we can define so this is the converse of this. So there exists a compactly supported function whose Fourier transform can define like this on a given Alphonse regular set. So this is related to the classical Barling-Malyavian theorem. Okay, so what is quasi-analytic functions? So quasi-analytic functions are the generalization of analytic functions. It says that whenever we have a function and a smooth function on an interval, and if at some point it has an infinite order 0, that function has to vanish. This is the definition of quasi-analytic class. Whenever we have a function in that class, if there exists a point of infinite order 0, that function has to vanish. To classify this class of functions, one consider this logarithmically convex sequence Mn, and then define the class. So this is a generalization of analytic class. So analytic class are given by those functions for which the Taylor series converge. So there should exist certain amount of restriction on its growth of its higher order derivatives. So this kind of growth will be controlled now by this constant Mn. So we have a function whose derivative has a control by Mn. Then Denjoy-Kernelman theorem says that, okay, if this Mn satisfies this Kernelman condition, this series is divergent, then this class Cmn will be quasi-analytic class. So if I consider Mn equals to factorial n, this will correspond to the analytic functions. And if Mn equals to n log n to the power n, so this is more general than analytic functions, still have this kind of unique continuation properties. Now I'll talk about the smallness result for quasi-analytic functions on RD. That was initially proved by Bourgain on R. Now I'll consider the same kind of result on RD. So here, this is a result by Jayan Matskovsky. So here, this weight theta will be replaced by general weight. So this weight satisfies two conditions: non-decreasing and log convex. And also that integral should diverge. That also says that weight should go to infinity, but rather slowly. But it is going to infinity, so that this integral is always diverging. Then this is the characterization of propagation of smallness on a relatively dense set. So for every dimension d and gamma and L, they parameterize the relatively denseness of set, and CW will parameterize the class of function that we will consider here. So we'll consider all those functions whose Fourier transform has at least this much decay. So we have a weight, and that weight multiply with the Fourier transform, this L2 norm still dominated by the L2 norm of the function. This constant C is appearing here. So we'll consider all those functions. Then there exists a constant C that will depend on the dimension and the relatively denseness parameter gamma NL, and this weight and the constant CW. Now, whenever we have a relatively dense set, I can recover the function f from its restriction on the relatively dense set. So this is the most general version of propagation of smallness of a function from a relatively small set. So here we are not considering the spectrally localized function. We are considering those functions whose Fourier transform has sufficiently decay. And I should mention the decay that was characterized in terms of the fact that when the function will be quasi-analytic, if its Fourier transform has a certain amount of decay, then the function will be quasi-analytic. So this is precisely the decay that appearing here. So this decay will guarantee that function is quasi-analytic, so that I can generate a local estimate for quasi-analytic functions. So initially I have started with a local estimate like Remy's inequality for analytic for polynomials. Then I have stated similar inequality for analytic function. Now I am saying that so there are certain results that is also holds true for quasi-analytic functions. This is the main ingredient to prove a relatively denseness propagation of uniqueness from a relatively dense like this. So this is the result. So this is the result of Nazarov, Sudin, and Bolberg, appeared in 2004. It says that whenever we have a quasi-analytic class, we have a function that belongs to a quasi-analytic class. This class is actually I already have defined its Fourier its nth derivative is controlled by the sequence Mn. Now, whenever we have an interval 0 to 1 and E is a subset of that interval, we can control the L infinity norm of the function h from its behavior on the set E. Now, the degree that appearing here is related to something called bank degree of a quasi-analytic sequence of functions. It also depends on h, and it depends on the sequence Mn. So if I take the polynomial, this will be reduced to the degree of the polynomial. So this is the main ingredient that one can use to prove that was proved by the earlier work in the context of higher dimensional Euclidean spaces. Okay, this is the other way of seeing this propagation of smallness, but not spectrally localized function. So now I'll pick up our result from this direction. So we'll consider a function that not necessarily spectrally localized. So if it is spectrally localized, there are a lot of work already have done in the context of analytic and smooth manifold. Now I'll consider Lie group, but I will not consider the spectrally localized function. I'll consider the function whose behavior is kind of quasi-analytic. So that is what now I'm going to define. So our setup is compact connected Lie group. So I'll start with the with few definitions. So for us, G be a compact connected Lie group with dimension D with Lie algebra script G. Then I'll consider an add invariant inner product on G. So this always exists since capital G is compact. So we can start from a left invariant inner product and then average it from the right. So we'll get add invariant inner product on G. It will induce a bi-invariant metric on the Lie group, compact Lie group G, and G will be a Riemannian manifold. And let L be the corresponding Laplace-Beltrami operator on G. Now I'll consider a ball with respect to this metric, obviously. Now G since is compact, so we'll equate it to the normalized Haar measure. Now how this measure looks like locally. So if I consider this measure locally with any point centered at G, then its behavior is some Jacobian with a geodesic distance from this point G, and then we have a surface measure on the ball, unit ball in the Lie algebra. And the behavior of the Jacobian is like r to the power d minus 1, and that is we can always dominate this r from lower and upper independent of the set X. So this is the local expression of the measure. Now I'll take any smooth function. I'll take a element from the universal enveloping algebra. Consider them as a left invariant differential operators. So this is the definition of left. So I'll take a element from the Lie algebra. Consider them as a left invariant vector fields. Now I'll consider as a product of Lie algebra's element and consider them as a element from this will also act as a left invariant vector field on the smooth functions. This is the definition of this action. Okay, so now I'll define what is called quasi-analytic class of function on compact Lie group. So given any logarithmically convex sequence Mn, we define the set C, M, and that also depends on the index P. So I'll consider the Pth norm. So we'll consider the smooth function, and if I apply the Laplacian, iterates of so this is the Laplacian, means this, you can also say this is the Casimir operator, iterates of Casimir operator acting on F, LP norm is less than equal to M to N. So since these are all second order operators, so I'll consider. Now this is the definition CMG. So I should put here P also. So CMPG are quasi-analytic if this sequence is diverging. So this condition is coming from the classification of the quasi-analytic class of function in the context of R. So we'll define it like this, and then we are considering this is the set of quasi-analytic functions. So this is just a definition. So we need certain kind of justification why this is a quasi-analytic class of functions. Of course, if f is an analytic function, one can show that this is true. But how can I say that, okay, if some function belongs to this class, it should satisfy strong unique continuation property. Okay, this is the result. So this says that whenever we have a function f, so this is the result that we will prove along the proof of uniqueness result. So f is a function in this class for some p, if there exists a point in G such that this enveloping algebra element acting on f vanish at G, and for all D coming from the universal enveloping algebra, then f has to vanish identically. So this is one hand related to the Chernoff theorem in the context of Rn. So that theorem we already have extended in the context of symmetric spaces. So this can be thought of an analog of this result in the context of compact Lie group. So here is some certain relation with the elliptic regularity theorem of Kota. Class of functions, and of course they will satisfy strong unique continuation property. Now this theorem can be generalization of that result in the context of quasi-analytic functions on compact Lie groups. So this is the class of function we have defined, and we justify the definition by showing that any function in this class satisfy strong unique continuation property. Now our aim is to quantify this fact. How can I quantify this strong unique continuation property? Can I say, okay, if we have a relatively dense subset of G, can we recover the LP mass of F out of its restriction on a relatively dense set? Okay, that is the result that we are aiming to prove. So first we will define what is relatively dense set in G. Okay, this is the definition. We have a parameter gamma, and then we'll say that, okay, a subset of G is gamma relatively dense if there exists omega should contain at least gamma portion of the mass of the ball, and this has to hold true for all G. So this is kind of gamma or relatively dense. Okay, so this is the definition of relatively dense set, and this is similar definition as we did for Euclidean spaces. Now this is our main uniqueness result. So okay, see, we have a quasi-analytic sequence Mn. We have two parameters, gamma that will quantify the relatively dense set, and we have a p that will be the LP norm that we are aiming to restrict. Then there exists absolute constant C. That C will depend only on G. Okay, so it is not depending on any of these parameters, such that the LP norm of the function on the entire Lie group G will be controlled by this constant C and then gamma. And then we have one more gamma 2m. So this function capital gamma 2nm, this will entirely depend on the sequence Mn. And this small gamma appearing on the right, this is related to the relatively denseness of the set omega. And then we have P norm here, 1 over P. And then we have the LP norm of F on omega. And this is true for all quasi-analytic class of functions. If I consider any gamma relatively dense set. Okay, so gamma relatively dense set is very important here, and you can see that I can restrict the function on any gamma relatively dense set. So it does not depend on the position or shape or size of the relatively dense set. It is only depend on the parameter gamma. So this is holds true for each and every relatively dense subset of G. Okay, so now our aim is to, so since we have a quasi-analytic quantification of quasi-analytic functions, now our aim is to prove a result that is analogous to Benjamin Jai and Matsuski result that appeared for RD in the context of RD for functions which are not spectrally localized, but its Fourier transform has certain kind of decay. So we are aiming to prove similar kind of result in the context of Lie group. So what is the definition of Fourier transform on the Lie group? Okay, so we have a L1 function with respect to the measure mu. Now I'll consider all irreducible and unitary representations on G that are equivalent, that will be denoted by hat of G. This is the representation space on which the Fourier transform will be defined. So Fourier transform are operator valued. So this is the definition of the Fourier transform. Now we have inversion formula, and from the inversion formula one can show Plancherel formula. Whenever we have a L2 function, we can recover the function f out of its Fourier transform by this formula. So this is the Peter-Weyl theorem. This is an application of Peter-Weyl theorem on a compact Lie group. So this is our analog of this result in the context of Lie group. So we have a weight, the weight, that kind of weight that I'll consider, that was already considered by them in the context of RD. So we'll consider a similar kind of weight. Now we have a parameter gamma, then we have a CW that will appear in the class of function that we are considering here. Then there exists a finite constant C that will depend on these three parameters, of course on G. Then whenever we have a function in L2 and is Fourier transform satisfy this much decay and omega is relatively dense set, I can recover the L2 norm of f on the entire Lie group out of its relatively dense set. So this is our second result in the context of Lie group. Now what about the Logvinenko-Sereda theorem? Okay, so Logvinenko-Sereda theorem, that was initially proved for any smooth manifold. So we can also recover that result on compact Lie groups. So I can take the spectral projection up to energy lambda. So this is the Laplacian. I'll take the spectral projection of it up to energy lambda. Then for any such kind of function, I can always recover its L2 norm from a relatively dense set. This will follow as a corollary of the above theorem. This is an extension of Logvinenko-Sereda theorem in the context of compact connected Lie groups. Okay, now I'll talk about some idea of the proof. So the proof need the following Sobolev inequality. It says that whenever we have a element in the Lie algebra, considering them as a left invariant vector field, if I take the iterates of that acting on f, its L infinity norm will be controlled by certain power of Laplacian acting on f, it's L1. That constant that is very important here, that is greater than 1, and of course it should be independent of n. That is also very important. Now if n is even, I can control it by this. If n is odd, then I can control it by this. So on the right hand side, I will always get a differential operator, not a pseudo differential like thing. So that's why I break it in two parts. So this is one of the main ingredients for the proof of the main result. So idea of the proof is to restrict the function on a geodesic curve, and then apply the one-dimensional quasi-analytic result that was due to Nazarov, etc. And their result we will use by restricting the function on a geodesic curve, and then with that curve will have certain amount of curve length that is positive, and then we can consider this Euclidean result, and then I can somehow manage to sum this thing to get the result on the group G. Okay, for the proof of the lemma, we'll use basically the fact that Laplace-Beltrame operator this will have a fixed eigen value for each matrix coefficient for all the representations. So that we can use to get this thing with some technical details there. So now I'll say a few steps towards the proof of the main result. So first one is first we'll cover the group by finitely many balls of radius r, that r will be governed by the same r that appear for relatively denseness of the set omega. Then its LP norm will be equivalent to the LP norm on each ball. If I sum them off, then I'll get the LP norm of the function. Now I'll call certain balls are good, certain balls are bad. So this idea was due to Kubrick. So this thing was used in the case of one-dimensional Euclidean space. So there also they prove something. Some intervals are good intervals, some intervals are bad intervals, and most of the mass of the function will be contained in the union of good intervals only. And in the complement of good intervals, that is the bad interval, there it has a limited mass. So therefore I can neglect that. So what is the definition of good ball? So it's iterates of Laplacian acting on F. It will be controlled by this Mn sequence. Okay, and then the LP norm of the function. So this is the definition of good ball. So now our aim is to work under this assumption that a ball is good ball, because it will mainly contribute the most of the mass. Now we'll fix a good ball, and then we'll choose a point inside the ball, a G0 point, with this property. So its evolution of the function at this point should be at least greater than equals to its average. Then we will consider all the geodesic curve segments starting from G0. And then I'll calculate the mass of the set omega, relatively dense set, intersection with B. So it has a positive mass, and that I can use this formula of the measure. So I can write it in terms of this geodesic polar coordinates. And then there should exist at least one direction at which this mass should be dominated by this thing. So since this is less than or equal to this quantity, so I'll take at least one direction which will dominate this. So in that direction, I'll consider the geodesic curve segment, and then I will restrict the function on this segment only. So this is the L. L is nothing but the segment, the length of the segment, which will be inside the ball, and I is that segment. And then one can show that, okay, the portion of the ball inside omega will be dominated by the portion of the set I and its intersection with the set omega. So this is the inequality that reduces the problem on the compact manifold to a problem in the Euclidean setups. And then I'll consider those set A for which this geodesic curve segment will be in this set. Then its measure will be this. And then I'll define the function by taking the projection of the function on this segment. Then we can show by using that lemma that this lemma will say that, okay, this function is quasi-analytic in the Euclidean sense, and we can dominate its L infinity on 0, 1 by its L infinity on the set A. Okay, there are certain things that we should remember, that this direction Y should depend on the point G0. If I change the set G0, if I change the ball, then the G0 will get changed and the direction will get changed. So these constants should be independent of the set of the direction Y. Okay, that are the things that we somehow managed to get. So we'll get this thing, and then the supremum on the entire ball intersection with omega will be greater than its restriction on the segment I, and then I'll use this inequality. And then I can get a local estimate on the ball, and then using the union of good balls, we can somehow manage to get our result. So in the case of compact manifold, to proving this kind of uniqueness result is related to the fact that we have somehow restricted it to the one-dimensional quasi-analytic function. Okay, now I will consider the homogeneous spaces. So mostly these results on the homogeneous spaces are coming from the result on the entire space. So, but we cannot directly use the proof statement of the result, but we can repeat the same process to get the result on the homogeneous spaces. So homogeneous space is nothing but, so we'll consider only closed subgroup of G, and Gy is the homogeneous space, and then the add-invariant inner product with respect to that we'll take the complement of H in G, that we'll call Q, and then we'll take the restriction of the Laplace-Beltrami operator on G over H. G over H is the Riemannian manifold, so on which this is the Laplace-Beltrami operator. And then similarly we can get the push forward of the normalized Haar measure on G over H, And then we can define this quasi-analytic sequence of class of functions on G over H similarly in terms of this Laplace-Beltrami operator. Now, okay, so since now functions sitting here has extra symmetry because they are now right H invariant. If we consider smooth function over G over H, then this function, if I consider them as a function on G, that will be right G H invariant, and its action, the main Laplacian acting of that lift of that function is same as its action, this operator acting on it. So therefore, any function, if I consider them as a function in G over H, this possesses an extra symmetry compared to those that we define in the case of G. So this will certainly give some help to consider the unique continuation result in the context of G over H. So this is the result. It says that, okay, so to obtain a unique continuation result, I don't need all of the differential operators that coming from the universal elliptical algebra of G, but I will consider only those which are coming from the algebra of Q. But I will consider them as a right invariant differential operator that will act naturally as a differential operator on G over H. So we'll consider the differential operator on G over H, but the collection is less because we have extra symmetry on the function space. So that we can manage to prove. So this is the unique continuation result, and that is the exact analog of Chernoff theorem in the context of homogeneous space on G over H. And this is our uniqueness result in the context of homogeneous space. A similar statement, so I can recover the LP norm out of its LP norm on a relatively dense set that is defined in the context of its metric on G over H. Okay, this is the more or less end of our findings. So this is our joint work with our with my student Sanjeev. So we are working on this project. So we have got certain result like this till now. Okay, here are certain references one can check. Thank you. Thank you. That's all.
Thank you, Mithunda, for a nice talk. Okay, so are there questions from the audience?
So for the homogeneous spaces, you still assume that G is compact?
Yes, G is compact. Yes.
And there is a Chernoff theorem in the background. You prove a Chernoff theorem?
We actually prove this result. Actually, proof of Chernoff's theorem in this context is a little bit easier compared to that we have done for other spaces. Because here we have an exponential function that goes from Lie algebra to Lie group, that is surjective. And using that fact, somehow we can reduce it to the Euclidean scenario. So
your formulation of these the classes CMP, then in order to show that is a quasi-analytic class, do you use Chernoff's theorem?
No, we have not used that. Our motivation is coming from there, but we have independently proved this.
Okay, you don't use. I thought you prove a Chernoff's theorem, and then because of that, it is a quasi-analytic class.
No, we have defined it like that, and then we are proving a Chernoff theorem. Of course, we define like this, and then we are proving a Chernoff theorem for this class of function. We are proving a Chernoff theorem here. Sir, we are proving a Chernoff theorem on compact Lie group and homogeneous spaces.
Are you somehow reducing matters to one-dimensional Dinjo-Ocker elements?
Okay, for Chernoff theorem, yes. For Chernoff theorem, we are reducing somehow one-dimensional Dinjo-Ocker element theorem. Yes.
Like Bochner did with heat, you did something else, but came down to...
Okay, but everything is we are doing by reducing it to the one-dimensional result. Okay, now we are working in the direction of, okay, can we do the same kind of result in the context of Riemannian manifold? Okay, so we have some idea, we are working on this direction, in this direction. And also we have one more direction that we already have proof Logvinenko-Sereda theorem for radial function on rank 1 symmetric spaces. So the result that I was talking about for hyperbolic plane, if I consider the radial function on the plane, that kind of result we have already done in the context of rank 1 symmetric spaces. Okay, we have a lot more general result for radial function on rank 1 symmetric spaces. So this is one direction that we are also working on, and this is one more direction towards the compact Riemannian manifold.
Are there any other questions from the audience? Okay, if not, let us unmute and thank the speaker for a nice talk. Okay.
Thank you, Muna.
Thank you. Kalachand, you may stop the recording.